Robert Kirshner is not a man who makes mistakes. Harvard astronomer, co-discoverer of dark energy, cited over 57,000 times in scientific literature. In 1981, he and his team at the University of Michigan were doing something no one had done before, building a 3D map of the universe. Not a drawing, not a theory, a real map. Coordinates, distances, depth. The map was taking shape. Galaxy clusters, filaments, the architecture of everything. And then, a blank. A region 700 million light-years from Earth where there should have been thousands of galaxies. There were 60. Kirshner thought the equipment was broken. He checked again. 60. He pointed other telescopes at the same region. 60. What Robert Kirshner found that day is still the largest known structure of its kind in the observable universe. And to this day, nobody can fully explain how it exists. To understand why this void is impossible, you need to understand how the universe is built. The universe is not random. At the largest scales, hundreds of millions of light-years, it looks like a web, a cosmic web. Imagine the world's largest soap bubble structure. Walls of galaxy clusters stretching billions of light-years, where the walls intersect, massive cities of thousands of galaxies. Between the walls, empty space, voids. This structure grew from the Big Bang. In the first moments after the universe was born, some regions were slightly, microscopically, denser than others. Gravity did the rest. Over 13.8 billion years, it pulled matter into those filaments, emptied the spaces between them, and created the web we see today. Voids are normal, expected, predicted by every cosmological model. Think of it like making Swiss cheese. The cheese is the galaxies. The holes are the voids. The process of making the cheese creates both. But here's the rule. The size of a void is limited by time. The universe is 13.8 billion years old. Gravity works at a certain speed. Matter can only move so far in 13.8 billion years. So there's a mathematical ceiling, a maximum size that any void can reach given how much time has passed. That ceiling is roughly 150 million light-years. The Boötes Void is 330 million light-years across, more than twice the theoretical maximum. In a universe that plays by the rules, the Boötes Void should not exist. It's 1981. Kirshner's team is at the University of Michigan. Their method is elegant. Every galaxy moving away from us has a redshift. Its light stretched by expansion, shifted toward red. The faster it moves, the farther away it is. Measure the redshift. Calculate the distance. Plot the position. Build the map. Week by week, the 3D universe took shape. Clusters appeared. Walls of galaxies. The structure was beautiful, ordered, expected. And then, a blank region appeared in the map. It was so large, so empty, that Kirshner's first instinct was instrument error. He wrote in his notes, "There is a hole in the universe." Then he crossed it out. Too dramatic. But the hole was real. At 700 million light-years from Earth, in the direction of a constellation called Boötes, the herdsman, there was a roughly spherical region of space approximately 330 million light-years in diameter. Inside it, 60 galaxies, where there should be 2,000. To understand the scale of 330 million light-years, our entire Milky Way is 100,000 light-years across. You could fit the Milky Way inside the Boötes Void 330 times in a single straight line. Or think of it this way. If you shrank the entire observable universe down to the size of the Earth, the Boötes Void would be the size of a football stadium. Standing inside it, looking out in every direction, the nearest galaxy would be so far away that for most of human history, if we had lived inside the Boötes Void, we would have had no idea other galaxies existed. We would have thought we were alone. The region was named the Boötes Void. Informally, the Great Nothing. Here's the part nobody talks about. The Boötes Void is not completely empty. There are 60 galaxies in there. But here's what's strange about them. They're not scattered randomly throughout the void. They're clustered, arranged in a thin filament, running like a tube through the middle of it, like a narrow road through an infinite desert. Astronomers call these void galaxies. Galaxies that exist in almost complete isolation, separated from the nearest cosmic neighbors, by distances no galaxy in a cluster ever experiences. One of them has been called the loneliest galaxy in the universe, Boötes Void. The galaxy inside the Boötes Void sits in a region so empty that the nearest large galaxy is hundreds of millions of light-years away. What does isolation on that scale mean? On Earth, isolation means weeks without human contact. In deep space, isolation means your nearest neighbor is so far that the light from it left before complex life existed on Earth, and still hasn't reached you. These 60 galaxies have been alone for essentially the entire history of the universe. And the void around them keeps growing. Because the universe is expanding, and the expansion is accelerating. The walls of the Boötes Void are moving outward. The void is getting bigger. The galaxies inside are getting more isolated. Every second, the great nothing becomes slightly greater. Science has an answer for the Boötes Void. It's not a satisfying answer, but it exists. The current mainstream theory is called void coalescence. The idea, what looks like one giant void is actually several smaller voids that merged over billions of years. Think of soap bubbles again. When two bubbles touch, the wall between them dissolves. They become one larger bubble. According to this theory, the Boötes Void grew from many smaller voids colliding and merging over 13 billion years. The math works barely. Simulations show it's possible, just statistically very unlikely. One study estimated the probability of a void this large forming by random chance and normal physics at roughly 1 in 10,000. Not impossible, just profoundly unusual. Most cosmologists accept this explanation, but there's a crack in it. Because on the other side of the sky, in the direction of a constellation called Eridanus, there's something else, something that the standard model can't explain at all. To find this second anomaly, we have to look at the oldest light in the universe. 380,000 years after the Big Bang, before there were galaxies, before there were stars, the universe was a hot, dense fog of plasma. Then it cooled enough for atoms to form. And the light that had been trapped in that fog was suddenly free. It scattered in every direction. It's been traveling ever since. That ancient light, cooled and stretched by 13.8 billion years of expansion, now fills the entire sky as a faint microwave glow. We call it the cosmic microwave background, the CMB. It's a photograph of the universe when it was 380,000 years old. When we mapped it precisely, using satellites like WMAP in 2003 and Planck in 2015, we found something that shouldn't be there. In the direction of the constellation Eridanus, the same general region of sky as a massive supervoid, there is a patch of the CMB that is colder than it should be, not a little colder. The average temperature variation across the CMB is 18 millionths of a degree. The cold spot is 70 to 140 millionths of a degree colder than average. That's roughly 4 to 8 times the expected variation. In statistics, anything beyond 3 standard deviations is considered significant. The cold spot is well beyond that. Our best cosmological model, lambda CDM, cannot produce a feature like this through normal physics. For years, scientists looked for an explanation. The most obvious candidate, a supervoid in that direction, blocking and draining energy from the ancient light as it passes through. They found a supervoid there, the Eridanus supervoid. But it's not big enough, not empty enough. It accounts for part of the cold spot. Not all of it. The remainder has no conventional explanation. In 2006, a physicist named Laura Mersini-Houghton was working on a problem in string theory. She was trying to answer a question that most physicists don't ask. If our universe began, what did it begin inside of? Her answer was the multiverse, not as metaphor, not as philosophy, as a testable mathematical framework. Her theory, our universe is one of countless universes, each born from the same quantum foam, each expanding in its own direction through a higher dimensional space called the bulk. Most of the time, these universes never interact, but Mersini-Houghton calculated something specific. In the earliest moments of our universe's birth, before inflation stretched it to the size we know. Our baby universe may have become quantumly entangled with a neighboring one. Quantum entanglement. The phenomenon where two particles become linked, their fates connected regardless of distance. Mersini-Houghton scaled this up. Not two particles, two universes. And she made a prediction. If this entanglement happened, it would have pulled energy from a specific region of our infant universe just before inflation blew it to cosmic scales. The result? A region of our universe that started with less matter from the very beginning. Less dense, colder, emptier. She calculated where this region should appear in the sky. She calculated how large it should be. She calculated how cold. Then she published her paper. 7 months later, Lawrence Rudnick at the University of Minnesota accidentally discovered a giant void while studying radio telescope data. It was in exactly the region Mersini-Houghton had predicted. The size matched. The temperature matched. Mersini-Houghton herself described what this means. It is the unmistakable imprint of another universe beyond the edge of our own. She said, "Standard cosmology cannot explain such a giant cosmic hole. A hole so large, so cold, so precisely located, that she had predicted it before it was found." The astrophysics community erupted. Some called it the most important discovery in modern cosmology. Others called it a coincidence. The debate is still open, because here's what makes this theory not just controversial, but terrifying. If Mersini-Houghton is right, that cold patch in the sky, that faint bruise in the oldest light in the universe, is not a statistical anomaly. It's not a measurement error, it's a scar. A physical mark left on our universe from the moment it brushed against another one. Before inflation, before galaxies, before stars, before any of this. Two realities, touching, and the evidence is still up there, written in the temperature of the oldest light in existence, visible to any telescope pointed at the right patch of sky. Science has a word for the current status of the cold spot theory: inconclusive. The Planck satellite measured the cold spot with more precision than any instrument before it. The results neither confirmed nor ruled out the parallel universe hypothesis. The super void in Eridanus is real. The coldness is real. The gap in the math is real. But the final proof, the smoking gun that would force every physicist to accept that we are not alone in a sea of universes, has not arrived. Not yet. What we have instead is this: a hole in the universe twice the size physics allows. A cold scar in the oldest light in existence that our best models cannot fully explain. A physicist who predicted both before they were observed. And a question that cosmology has been circling for 2 decades without being able to close. What if the void isn't empty? What if it's a shadow? The shadow of something that was here before our universe had a name, before it had galaxies, stars, planets, or people, before it had anything at all. Robert Kirshner spent his career mapping the universe, measuring distances, charting structure, building the most precise 3D picture of the cosmos ever constructed. In 1981, he found something that didn't fit. He called it a hole. Then he crossed it out. Too dramatic. He shouldn't have. Because 44 years later, the Boötes Void is still there. Still growing. Still unexplained. Not by the standard model, not by the best simulations, not by the most precise satellites we've ever built. The universe contains something for which we still do not have the right words, a place where the rules we use to describe everything quietly stop working. We named it the Great Nothing, but that's not quite right either. Because nothing, true, absolute nothing, would be easier to understand. This is something else. Something that sits at the edge of what physics can say. Something that, on its worst days, makes physicists wonder if our universe is the only story being told. Or just one of many. And we can't see the others. We can only see the bruise they left behind.